Hi, this is Terry Dennery of the MathWorks. Um, so let's begin where we left off on the last video. And so we add this inverse DC motor, essentially a feed-forward control strategy, right? And we'll see that we did really well, right? And so the basic idea is how do we bring this to hardware? This is simulation, and so I'm going to go back to the model that we kicked the whole thing off with in our first video, and bring our attention to the DC motor interface that we created with the Arduino blocks, right? And in this video, I do want to explore a little bit of the idea of increasing the rate at which we're going to update things. And I want to make things as easy as possible on my Arduino processor. So I'm going to even remove that, all right? And the basic idea of this video is to simply keep that hardware interface, get rid of everything else. So all of this we're going to essentially put in place, right? And I'm going to do a little bit of bookkeeping here, or let's call it cleaning up, right? And so all this stuff that represents the overall control algorithm, I'm going to load that into its own subsystem, all right? And I'm going to do a little bit of let's call it cleanup, all right? And let's make it a little bit bigger. That looks pretty good. Let's move that up like that. Move that there. And let's give those ports better names than 1, 2, and 2. Okay, so we'll go inside. And I like that name. I want to give these better names. Let's move that over there. Let's move this over here. This you can see is essentially picking off the first component of the commanded motion, which I know to be the angle. Oops. And so we'll label it as angle CMD for command, right? And this is the angle feedback, right? Let's move that like that, and that's looking pretty good. And then finally, we'll call that V for voltage, right? And so essentially, there's our feedback thread. Here's our feed forward. They're added together, and that their sum will be what will be delivered as the voltage command for our motor. So all that looks pretty good. I always think it's a good idea to give things names. And maybe I'll call this plant model. Okay. All right. And so it's always a good idea, even if what you're doing seems like very cosmetic changes, hit the run button, make sure you're getting the same results, which we are. Okay. So with that, we're ready. All right. And so I'm going to Control C, copy this. Let's move this out of the way. Let's get here, and let's paste it in. Okay, so that voltage will be delivered to our hardware interface. We'll do the comparison between the angle command and the angle measured by our encoder, and we'll also feed back that encoder measurement. So with that, we've redefined the test with this better controller, and I think we're ready to try it out. So that looked pretty good. Went a little bit slow, and you can see that this is set up with our slower transition. So that's the 3-second transition, which we saw we did very well with, really with both pure feedback as well as feedback plus feed forward, right? So anyways, let's switch to our harder problem. And so we'll make the transition take place in 3/4 of a second. And we'll run it again. Okay, so much faster, and we'll compare. And just like we saw before, still a little bit of overshoot. I think it looks good, all right? And so Anyways, what I would like to do now, though, is to kind of redo this, but let's do it with this idea that, well, there's always hardware solutions too, right? And so what I'd like to do, I'll do, you know, um, useful editing so we can kind of move through this quickly. But what we're going to do is, and I'll reveal this to you a little bit. So, essentially there's timing to all this, and you'll see that, for the encoder example, there is a TS. You recall we put in a 0.01 before, and similarly, we have a TS. I believe we do. Oh, we don't. So let me move this over so you can see it. But let's go ahead and put that in. And since TS was already equal to 0.01, we wouldn't get a different result for the current value of T sub S. But then the final thing is that I set my solver for the whole model to be T sub S too. All right, and so what I'd like to do is run this 3 times faster. So instead of being 100 hertz, now it'll be 300 hertz. All right. And I think I'm going to do this now in that same order that we did it in the initial demo, which is let's run it with pure feedback. Let's then run it with feed forward and kind of explore the impact that way. So all I'm doing this time is merely commenting out that component. It sends a 0 into the sum, therefore that's pure feedback, right? So let's hit run. Ooh, one more thing. We want to compare all these. So let's log the measurement. So measured angle is what I'm going to name this signal now. So I'm going to right mouse click on this and log the signal, and you'll see the little antenna right there. Right, and that means that we can send it to our data inspector. You'll see that I did some practice runs, so there's a bunch of stored up stuff right there, but let me delete that. Yes, and let's delete this one too, which was, I guess, our last run. Right. All right, I think we're ready. That's a little slow bringing that to the camera. Sorry about that. But let's see how we did. All right, and so again, this is pure feedback. And what we're seeing, even with that much higher rate of 300 hertz, we're going to still see that same lag, and we're going to still see quite a bit of overshoot. Not sure if it's reduced at all. Let's measure it. And it's pretty close, maybe 5 degrees better, right? So it looks like we're about 75 degrees overshoot. And if you recall the first video, we're at about 80. So, and I'll just speak a little bit from experience. Certainly I work with lots and lots of controls engineers doing really amazing position control. And I think they typically will operate more on the level of like 10,000 hertz. So there are things that you can do to get those higher rates, but generally you don't do it with an Arduino. You'll use like DSPs and more expensive processors. I even see people using FPGAs because they can really maximize the rates with those. Okay, so anyways, what I'm going to do now is kind of model kind of what uh, controls engineers can do, right? And I love that I was able to hit this auto tune button. It kind of got me in the neighborhood, but I also know my friends who are much more studied in controls than me that have a much better sense on how to adjust these parameters. And so I'm going to just kind of, for an example, let's increase the proportional gain. So this could be 3 times higher this time. Here we go. Okay, so where that rate didn't help us so much, certainly this helped us quite a bit. And so that higher proportional gain, and that's what controls engineers and people who simply, understand, I'll call it linear response, can be extremely helpful to tune these things. And so we're now operating about 20 degrees overshoot. And so the final thing we're going to do is let's put that feed forward component back in there. All right, and so we'll go into the controller and we will uncomment that, and we'll do one more run. Okay, there we go. That looked pretty good, didn't it? So let's see how we did. And you can see we're down to maybe about 4 degrees, but boy, that looks good. All right, and to be real clear on this, that our customers do amazing things with regard to position control, and certainly I've experienced numbers of them, hitting like 10th of a degree accuracy and better, and it's a lot that can be done there. And so, anyways, I think the way I'd like to wrap up this video is let's move to our data inspector. You'll see the last 3 runs are logged here. And I think I'll go to the first one right here, measured angle. Right, so this is the one that's close to, I think, 75 degrees overshoot. It is at 300 hertz, but it's completely pure feedback. Right, now the next run, right here, run 2. I think I'll change the color on this one. Let's make this one blue. We'll put that in. Was about going to our controls engineering saying, hey, can you kind of tune up those gains, which they did. And let's see, zoom in Y, just kind of look at this level. And that led to about, substantial increase. So essentially KP being 3 times bigger. And so then finally, let's put this last one in, and let's make this one kind of a burnt orange. And here you're seeing we're nailing it. Okay, so I think the overall conclusion is there's lots of ways to kind of get it to work. Me personally, I'm a big fan of this idea of using what you know about the motor, come up with kind of the feed forward approach, which is really your means of taking what you know, and using that to estimate very accurately what will be the requirements in this example of what the voltage is that will make it move the way we want it to. But I just look at that and go, wow, pure feedback, getting a response. I'll call it linear response kind of controls expert involved in optimizing the feedback and then adding to that the feed forward piece. There are remarkable things that we can do. So anyways, it's been a lot of fun doing this series, and it really is quite a thrill to work with real hardware and to see these ideas that we've been working on via simulation that they can really happen, in the real world too. So thank you.